Hello, everyone. This is our second to last lecture of the semester. Yay. This lecture is on basically Chapter 15, which covers oscillations. And specifically, this part of the lecture is going to cover what are called pendulums. So an oscillating system is a system that the motion repeats with some periodicity, meaning in some finite time, the system's motion repeats every so often. We're going to study pendulums first because they're easier, and then we'll move on to other systems. However, this is really our big wrap-up lecture. I maintain that everything that we've learned all semester basically gets wrapped up into this lecture. We're going to use everything that we've learned, everything I've tried to teach you, everything I've tried to tell you, I'm going to try to emphasize in this lecture and show you what we've learned. Pendulums are super simple, but they describe a lot of physical phenomena. They're really cool, they're really easy, and they tell us some neat things about how the world works and how systems work. So, first of all, we need to talk a little bit about the physics. Before we can talk about pendulums, we really need to understand an oscillating system and the math that we use to build on it. Turns out there's a neat little trick that you can use to figure out the period of a pendulum, but in order to do it, you need to do some other stuff first. So we need to look at what is called a system with a restoring force. So let's imagine we have a system that we're going to model as some point mass that's like a block. So this is just some mass m, and it's connected by a spring, and it's at an equilibrium point. So we say that when the spring is unstretched, it's not compressed, it's not stretched, it has a rest length of L, and the block would therefore be sitting at an equilibrium point called x is equal to 0. So this concept relies on something called an ideal spring. That's what's going to supply our restoring force. An ideal spring has a spring constant that we call K. The reason why it's an ideal spring is we assume K is constant. No matter how much we stretch or compress the spring, K never changes. Okay, and we're not worried about the mass of the spring. Remember too that all semester, what we've been trying to do is figure out how to make predictions about the motion of an object or a system. So this idea is we need to figure out what the motion, how fast and at what position, what displacement this block has if we start by compressing or stretching the spring a certain distance and let it go. What will happen? Okay. And so what we're going to say is that imagine we, first of all, pull the block some distance x out. Okay. We pull it some change of x where this is what I'm going to call x max. And remember that x max is positive. And we hold it there. What does the spring do? So the force of the spring is going to try to pull it back that way. We know this from experience. And this force is going to be kx. But we can see here that if we assume that x is positive in that direction, this will be a negative. This restoring force from this spring is negative. Second, imagine you compress it. So you push this spring in so that now it's at some delta x, but this is negative x max. So it's some maximum x. The force due to the spring is going to try to push it back towards equilibrium. And so the force due to the spring is going to be minus kx because x max is minus. So this is going to be minus kx. So this restoring force always has a magnitude of some k, some spring constant, times x, but it's also always negative because it's always trying to fight the displacement of the object. The force is always opposite of the displacement. That's why it's a restoring force. This actually models any system that when you perturb it or move it a little bit away from equilibrium, it tries to move back to equilibrium. So this could be gravity. This could be a protein on a molecule that you kind of pull the protein away and the molecule pulls it, or cell pulls the protein back towards it. It's anything that tries to come back to equilibrium if you disturb it. Note that there's no friction, there's no other forces acting here. And a restoring force is actually conservative. It's like gravity. Gravity is a restoring force. It's trying to pull an object back to the center of mass of the gravity. So anytime we have a restoring force, the force is negative kx. That's all I want you to get out of this right now. But I wanted to show you where the negative comes from and why it's always a negative. Unlike friction, friction's always a negative because it's always pulling energy out. This is always a negative because, or friction is actually always negative because it's always going in the opposite direction of the velocity. This is a negative because it's always in the opposite direction of the displacement, okay? All right. What is the energy associated with a restoring force? Now we know that the work done by a force is F times dx, or F dot d, right? We could put a dot if we wanted to. But this is called the potential energy of a spring. It is the work done by the spring. And from x initial to x final, if we plug in for F, negative kx dx, we can easily see that this integral is going to be negative kx squared over 2 from x initial to x final. We also know that the work is the change of kinetic energy. So the potential energy, the change of potential energy, I should really say this is a change, is equal to the change in kinetic energy. That gives us that mb final squared over 2 plus k, let me back up for a minute, minus mb initial squared over 2 is equal to, notice that this is negative kx final squared over 2 minus a minus kx initial squared over 2. And by conservation of energy, which is why this is in fact a conservative force, we only care about the endpoints, and therefore the energy initial is equal to the energy final. By moving the initial kinetic energy over and the final spring energy over, we get that mv initial squared over 2 plus kx initial squared over 2 is equal to mv final squared over 2 plus kx final squared over 2. And what this is really saying is that if we look at 3 different points in this motion, we look at when it's stretched to negative x max, and when it moves back to equilibrium, and when it moves to x max. So when the displacement is negative x max 0 or x max, let's say we pulled this out and we let it go. It shoots this way, stops, and then shoots back. Couple things here. At this point, we know that v is 0, and at this point v is 0. Here, because x is 0, if the energy at any time is mv squared over 2 plus kx squared over 2, if x is 0, then we know that v has to be a max here. So this is all kinetic energy. This is all potential energy. This is all potential energy. And what we see is happening here is as it moves back and forth, as it oscillates, it's exchanging potential energy for kinetic energy, and then it's exchanging it back into potential energy. Just like throwing a ball up and down, all kinetic, all potential, all kinetic, you could go back and forth. We covered this chapter 7 when we talked about springs. I'm just reviewing this for you. The last thing that I want to mention right here is one cycle is when it goes all the way back to where it came from. So if we start here, one cycle is to go all the way to the left and come back to the right. If we started here, it would go, assuming it had velocity here, it would go to the right, come back to the left, and come back. So one complete cycle is when it returns to the initial point. That's kind of important. That's called the period, and it's how long it takes it to complete one cycle. All right. All of this, all I'm showing you it for is you should remember this. We're going to go over this more in our final lecture when we talk about oscillating systems, because we're going to need energy to understand how things work. However, what I want to say here is, yeah, we can use energy and figure out what the velocity and the displacement of this system is, but we can actually do better. It's kind of hard to tell what the velocity and position are at any time without knowing what the total energy of the system is at some time, and we could honestly find that if we wanted to, but there's a better way or another way to figure out what the displacement of the particle is at any time and what the velocity is of the particle at any time. So doing that is something called a differential equation. Now, I know some of you have had differential equations and some of you have not. And differential equations may seem scary. You might have heard how difficult it is. Well, I'm going to tell you, number one, we've been doing differential equations all semester. We just didn't act like we were doing differential equations. Almost everything we did, anything we did with acceleration or velocity was a differential equation. The difference is that when you do differential equations, you usually have to solve by finding a function and then taking the derivatives of that function to figure out if you have a solution. In a lot of ways, differential equations is a lot like a physics class more than a math class, because what you're taught is a bunch of different types of differential equations, how to recognize what type of differential equation you're trying to solve. And then you have a toolbox of strategies that work to solve that type. And there's a few things, theories and ideas in differential equations, one of them being that if you can find the solution, that's the solution. So any solution you find, if you find it, if it works, great. So you can essentially guess, and that's what we're going to do here. We're going to guess a solution based off of what we know and see if it works, and if it works, great. Okay, so let's look at what this differential equation is. Now, one of the first things that we learned were free body diagrams. And so let's use a free body diagram to get our force equation. If I don't want to do that. If I pull this block out initially at some x max, okay, I know that there's a force acting on it moving that way, and I'm going to assume that x is positive that way. If I draw my free body diagram, I have this force, and that's the only force acting. I could say that I have a normal and I have a weight. I don't really care about those, so I only care about this spring force. So MAX is equal to minus KX. My spring force is in the negative direction. It's minus KX, right? Okay. So really what I have here is I have A as a function of t is equal to minus K over M times X. I'm going to write this a little bit weird. What I really have is I have A as a function of t is equal to K over M times negative of some function. So I have a constant times the negative of some function gives me the acceleration, but what is the acceleration in terms of a derivative? Well, it's the second derivative with respect to time of my position function. So I need to find something that is if I take two derivatives of some function, it has to give me back the function and a constant and a negative sign. So if I take the second derivative of a function, I need to get it needs to become negative, and I need to have some constant out in front. That constant I'll be able to set equal to k over m, and therefore I'll know what it is, okay? And you might say, well, I have no idea what function that the second derivative is going to give me the function itself back. Well, you actually do. One of the really nice things about physics and biology and chemistry and humanity in general is that most of the systems we care about are periodic. And if they're periodic, we have some really easy periodic functions that we all know, that we're all familiar with. The two that we're going to use are sine and cosine. So if we let x of t equal some maximum value of x times either cosine of omega t, and the omega is just some angular frequency, and sine, okay? It doesn't have to be either one of these. In fact, how we really write this is we would write theta as omega t plus some phi. But this phi we're going to get into next lecture. This phi just tells me where I'm starting. It's a phase angle to tell me, for example, if I was starting at negative x max, this phi would be a certain value. Turns out it will be 180 degrees. I'm going to assume, however, that at t is equal to 0, I'm starting at x max. So at x of 0, that just means x at times 0, I'm at positive x max when t is equal to 0. Okay, so let's double check these derivatives really fast. If my function is x max cos of omega t, and if my function is x max sine of omega t, and remember that I'm looking for something that if I take the second derivative, it has to equal some constant times a negative times x of t. So I'm looking for something that gives me back a negative and something out in front, and the original function x max cos or x max sine. The first derivative of x with respect to t here, x max is a constant. When I do the chain rule on this, I take the derivative of what's inside, so I get an omega out, and then I take the derivative of the whole function. And this function, the derivative of cosine is negative sine. So I get a negative, and I get sine of omega t. This is going to be negative, x max times omega times cos. The derivative of sine is cosine without a negative. And then the second derivative, the derivative of sine and cosine. So this is omega squared. I get another factor of omega times x max times cosine of omega t. And here, I will get cosine becomes negative sine. I get negative omega squared x max sine of omega t. And so you might say, oh, they both work. My c here is omega squared, and I have a negative x max cos t, which was my xt, or I have omega squared and a negative x max sine. Either one works. But we're going to assume that since t was 0 and x of 0 had to be x max, let's look at this. So we're going to assume that those functions don't work, because if I put in a 0 here, I get 0. So these aren't adding anything here. We're just going to assume that we have some cosine of omega t. And this, it turns out, is what we want, okay? So we got that d squared x of t was equal to dt squared was equal to minus omega squared K over m times x of t, and that was equal to negative omega squared x max cos omega t, right? This is obviously x max cos of omega t. So we're saying that this is x max cos omega t. And therefore, what we get is we get that omega squared is k over m, or better yet, that omega is square root of k over m. This, right now, you need to pay attention to. This I'm going to write a little f and a little f, okay? Because this is something called an angular frequency. This is the one point that I'm going to make later that you're going to see where you can get really messed up. But I want to pause here and talk about what we've actually been doing all semester. And all semester, what we've been trying to do is we've been trying to describe the motion of a system by developing some mathematical equations, which we could use to predict what the acceleration or the velocity was, right? So basically, we were creating a mathematical model of reality to interpret things. You may notice that when we talk about this block sliding back and forth, right, from negative x max to x max, as it goes back and forth, right, there's no angle involved here, right? So where does this omega that we've always seen as the angular velocity come in? Well, there is no angular velocity on this system. There is something called a frequency, though. And where that comes from is, we need to imagine a couple things. So this block, I'm going to start off at time is equal to 0 is at x max. So this is at 0. And then at t to the fourth, it's here and it's moving that way. And at t to the half, it's at x mass with a negative, stops, and it's moving back the other way. At 3/4 t is back at equilibrium. And finally, at the end of one complete period, it's returned to x max, right? So one complete cycle is it starts on the right, moves to the left, and comes back to the right. So let's draw that in an x versus t graph. So x, 0, negative xm. This is 0, this is t to the fourth, this is t to the half, this is 3/4 t, this is t. And it starts at x max, hits here, comes back the other way, it comes back. We could add 5/4 t, right, and it would be here. And so what we see is that this thing's doing, this thing going like this, right? And notice this is a cosine. This function is described by a cosine of some omega t. The omega f that we found that is equal to k over m is the speed at which the position function changes. So omega, this cos omega t factor gives you a factor from 1 to -1 that you can multiply the maximum amplitude by in order to figure out where it is. And what this omega is how fast that displacement is changing, but there's no angle, no physical angle that we're talking about. We're not taking a point here and saying, oh, we're now 45 degrees from this point. There's no physical angle here. What it is it's the frequency of the function. Because the function has to, because it's periodic, it has to change between 1 and -1. And omega tells you how fast, basically, the function changes from maximum to minimum values. But there's no angle associated with it here. It may seem like I'm being weird or pedantic or overly exploring this. I don't want you to mess up when we start talking about pendulums. We're going to have an angle. And I don't want you to confuse this with the actual angular velocity, how the pendulum rotates. This is the speed of the cosine function, which is governed by the period. Another thing that we can say is that the period is 2 pi over this omega f. So the period here is going to be 2 pi over k over m, or m over k, right? That is how long the period is of the oscillation. So one cycle, that's how long one cycle takes for a mass subject to a restoring force kx. That's all well and good, but just remember that omega is not a real thing. It's not imaginary. It's a description of the function of the displacement, and isn't real in that sense. In fact, omega is always a constant value, as you can see here. We assume k is constant, we assume m is constant, omega is constant, right? And you're going to see in a pendulum that the angular velocity is going to change, because if I'm swinging back and forth, I'm going positive, negative, positive, negative, positive, negative, and I'm going to 0. Therefore, the angular velocity can't be constant, but the angular frequency, omega f, is, okay? It's a trouble spot that some people have. They want to use omega to figure out what the angle of the pendulum's at, and that's not true. All right, so we're going to talk about pendulums now. I'm assuming that some, if not all of you, have had some physics before where they probably talked about a pendulum in high school, wherever you had it. In fact, you may actually know already that a pendulum has a period of L over G. I want you to try your hardest to not remember this. So most of, well, let me put it this way. You have all probably heard a lot of physicists talk about just derive the equation. Just derive the equation. Just get used to deriving it. Essentially, if you know the physics, you can derive for yourself the equations that you need without memorizing anything. That you don't need to memorize much, really. I mean, you need to memorize things like mv squared over 2 is kinetic energy, but you could even derive that. There are ways, okay? I want you to really try to learn how to derive this for yourself for any pendulum. That's the point of this chapter. That's why we're doing this part on pendulums by itself, is I want to show you how to derive the period of a physical pendulum and realize how that gives you immediately a simple pendulum. But this is a simple pendulum, and it's not that useful. It's only useful for a simple pendulum. A simple pendulum is a length of string with a mass m connected to it. It can rotate, okay, back and forth. And we're going to say that if originally it's some angle phi, then this is negative phi. So it's going to rotate through an angle of 2 phi. It's going to swing over to here and swing back. And that is one period, when it goes all the way and back. So it goes all the way to the right and comes all the way to the left and comes back. We've already seen a ballistic pendulum. One thing to note is a little bit of math variables. Okay. When this thing is crossing through the center line where phi is 0, right? This distance here is actually L minus L cos phi, because this distance is L cos phi. You can see that there, and this whole distance is L, the whole length. So the height if we assume that the height here is 0, and we assume the center of the Earth is that way, then the height here is L times 1 minus cos B, right? That's just a little bit of geometry that we need. Easy enough to understand. Remember that this is phi, and that omega of phi, we don't know. And it's definitely not constant. We can figure it out. We could actually figure it out because the energy at any time is equal to mgh, whatever this maximum h is. I should really make this big H. And then the energy at any other time is mv squared over 2 plus mg, whatever little h happens to be. So if you knew where it was at like half h, you could figure out what b was. And if you knew b, you can figure out that omega, because omega is v over r, where r is out. I'm not going to get into that. That's stuff we did with maybe the ballistic pendulum. You could have a problem on an exam with it, or even a quiz with it, but I don't care about that so much as I care about deriving the pendulum. Just know that all this applies here. We really say, oh, we just have this period equation, but all this other stuff does apply. Okay, so we need to come up with an equation of motion for the pendulum. And what we're going to do here is we're going to draw a free body diagram and a torque diagram, just like we did before. So the only force acting on this is mg. There is a tension here due to the rope. We don't care about that though. So this isn't going to help us much because we're going to have to figure out angles and stuff. We're not going to do that. Instead, let's look at the torque. The axis of rotation lies at a distance, I'm going to call this r, but this is equal to L. And the force acting on our mass is mg down, okay? There's a tension back along here, but for the torque, that doesn't matter because it's parallel to the axis of rotation, or in the radial direction of the axis of rotation. R and tension are parallel, so we don't care about it. But let's actually draw the torque diagram, and we note that this is our perpendicular because the torque is r cross F, which is r perpendicular F, and r perpendicular is, I'm just going to write it as, if this is phi, then this is r sine phi, and this force is mg. And we see that it's a negative alpha, right? Okay, so our torque is going to rotate it in a negative direction. So we're going to write that the torque is, if we remember, torque is I alpha, and therefore it's equal to, that would be negative. So we would get here a negative r sine phi times mg. But I want to rewrite this. I want to write this as alpha is equal to mgr over I with a negative sign times sine of phi. Okay. Now, when I look at this, I know that alpha is actually the second derivative of phi with respect to time. That's what alpha means. Secondly, as long as I have an angle less than 10, for angles less than 10 degrees, we can use that sine theta is theta, approximately, and cos theta is approximately 1. That's the small angle formula. It applies as long as essentially the angle is 10 degrees or less. So we're going to assume our pendulum is originally pulled out no more than 10 degrees. Pulled away from the center, no more than 10 degrees. if we do that, our sine phi becomes phi. Now, looking at this, I get that d squared phi over dt squared is equal to minus mgr over I times phi. And if I look at this, this was the same as my d squared x over dt squared is equal to minus some constant times x. Therefore, I can assume this is the same exact form. Not even assume, this is the same exact form. Therefore, I have an angular frequency that is equal to mgr over I with a square root. Because this part right here is my omega squared, right? And if I have that, then I know my period is going to be 2 pi over my angular frequency, which is 2 pi times I over mgr. And that right there is the period of a physical pendulum. It's the period of any pendulum. T is 2 pi moment of inertia I over the force of gravity times the radius of gyration, period. That's it. We're going to see how we're going to use this equation. We're going to do different things for it. But I would much rather you remember that equation than the equation of the simple pendulum. The reason why is this is saying that if I take the moment of inertia and I divide it by the force times the radius of gyration, the distance that that force is being applied, I get the period if I take the square root, right? It doesn't seem easy the first few times to remember it, but once you get it down, it makes total sense. And it might help to understand it from the point of view of a simple pendulum. For a simple pendulum, we just have a little mass at some distance, r is equal to L, at some phi, okay? And as we said, the period of this is 2 pi I over mg r. Now r here is L, but what is I? What is I for a point mass? If we assume this string has no mass, stretchless, frictionless, massless, what is I for a point mass? Well, it's m r or L squared. So here it's mr squared, which we said is ml squared. R is obviously L. So what I get is I get 2 pi ml squared over mgl. And that turns into 2 pi, one L cancels, the M cancel, and I get L over G. And I've got my simple pendulum. That is the period of a simple pendulum. It seems pretty easy, but it's not. We need to talk about a couple things really fast. I'm going to try to do the next part a little fast, but you don't have to pay a lot of attention. The next part that I want to talk about, just remember that the overall point is the angular frequency of how the function changes, how the displacement as it passes through one cycle, the angular frequency is always constant. But you can see that the angular velocity, at least for a pendulum, can't possibly be. To illustrate this, there is going to be so let's say it moves like this. Here, it stops. So V is equal to 0, omega is equal to 0, where this is the rotational omega. And here, V is going to be maximum. All the MGH turns into all V, and therefore omega is also maximum, because omega is simply V over R. And then here, V max is 0, or V is 0, and omega is 0. They're both 0. right? However, if this is some function, some cosine of some omega t times the maximum height, right? If this is what our y of t is, which it is, this omega, this frequency omega, is constant. And this frequency omega is actually equal to G over L. That's a constant. And that tells us how long it takes to go from this max to this max and back. So to go from h to negative h and back to h. It does that in a time of 2 pi over t, right? So how long does it take to get t out of this? That's what omega is telling you, right? We'll talk about that more in a second, but just to be clear, this is the frequency of how fast it's moving through a cycle. This omega r tells you how fast the position phi is changing. And this can vary. This omega phi or omega r, whatever you want to call it, this angular velocity can vary. It changes direction. This omega up here is a constant, and it's always positive. It's just how fast, it's a frequency. So it's 1 over seconds. It's how fast the period is changing with time, or whatever, how fast the radians are changing with time. Okay. So let's look at that again. I made this little chart, and we're going to assume that originally the pendulum starts off pulled out at an angle of 10 degrees, and this is my phi. So it's pulled out at an angle of 10 degrees. Quarter of the way through the period, it's here. Halfway through the period, it's here. 3/4 it's here. Full period, it's back, right? So you can see that the angle starts off at 10, goes to 0, goes to negative 10, back to 0, back to 10, back to 0, back to 10, right? However, if we look at the actual height, right? Okay, so height, well, we can do it actually angle. So we can go 10 degrees and minus 10 degrees and 0. And if this is 0 and this is t to the 4th and t to the half and t to the 3/4 and t and on and on and on, right? We know that this at t to the 4th is going to be at 0, and then at negative 10, and then back at 0, and then at 10. And so it's this sine wave that I didn't draw very well. I mean, it should look something like this, right? And this function is basically 10 times sine of omega t, or technically, I guess it's cos of omega t, right? And the omega associated with this is always just a positive G over L. And that's just how fast it's changing from 10 to minus 10 back to 10, right? But it's how fast the amplitude's changing. This omega can actually go to 1,000,000 rad if it needs to, or 1,000,000 rad per second. This omega is going to always be however far it traveled over t, but this omega can be negative or positive. This is the angular velocity, how fast it's swinging back and forth. It's not the same as the frequency G over L. Just don't make that mistake. G over L is a constant, always, okay? G over L, in fact, is equal to 2 pi over t, which we already know. Therefore, the period is 2 pi times L over G. We already know that, right? But the actual omega is going from 0 to maximum in the negative direction, 0 back to positive, 0 to negative, on and on and on, right? It's constantly changing. It looks like you should be able to get information of one from the other, and probably you might be able to figure out some relationship between the two. But just know that they're not the same. They're not the same omega. That's all I want. Okay, so let's talk about a few easy examples. So what is the point if you have something like a simple pendulum? What good is a simple pendulum, right? Well, let's say I want to make a 1-second clock and all I have is a mass and a string, okay? How long of a string would I need for, say, a 5-kilogram mass? So let's say I have a mass of 5 kilograms and I don't know what L is, but I'm going to pull this thing 10 degrees out and I'm going to let it go. And I'm standing on the surface of the Earth, so G is 9.81, and I want the period to be 1 second. So I need to solve this for L. And what I get here is I get T squared is 4 pi squared L over G, or L is G T squared over 4 pi squared, right? Okay, I know that T is 1, this is 9.81, this is 1 squared, this is 4 pi squared. All right, so 9.81 divided by 4 times pi gives me 2.48 or 0.248. So 24.85, 0.2485. So I need 24.85 centimeter long string. You can actually try this at home. Get a ruler, make a 25 centimeter string, tie it to your finger, tie a little mass to it, and start it swinging from about 10 degrees. And count how long it takes to go right to left to right. And it should be about 1 second. So if you were in the Middle Ages, you could make a clock, assuming you could make it frictionless at the pivot point, and with enough stuff that could accurately tell time for at least a while, maybe an hour, let's say. Pendulums are remarkably good for telling time in pretty long intervals. But you could make a clock basically with a pendulum. You would have to reset it every once in a while, but it would totally work if you knew G. It doesn't depend on the mass. If I put a 1,000,000 kilogram mass on this, I would still get a second as long as the length of the string was 0.2485. However, if I took that string up to the top of like Mount Whitney or something, where G starts to change, if G increases, right? So if I take this same pendulum to Death Valley and G increases to say 9.87, my pendulum actually moves faster. The period becomes less. A smaller period becomes means that it's moving faster, right? It's completing the cycle, going right, left, right, faster. If I was on the surface of the Earth and I tried it and my period was, let's say, 1.5 seconds, what would that tell me? That would tell me that G, for whatever reason, isn't 9.81. That in fact, G is smaller than 9.81. If gravity is reduced, then the period gets longer. And you could actually use this to figure out what the density is below you. If you had a really sensitive pendulum, you could tell what the gravity was below you, the density of the Earth below you, and from that, you could find things like oil. It's how they do geophysics type stuff, is take a pendulum. You can basically use a pendulum as a timepiece, a watch, that works using whatever local gravity is. So you could find local gravity, or you could measure seconds. And that's pretty rad for a piece of string and a rock basically in your pocket. Obviously, air pressure and friction in the string would affect you, but for the most part, you can do cool things with it. So I want to talk about one other example. Imagine you were an astronaut and you land on a planet that has a radius that is equal to 1/3 of the Earth's. You don't know what the mass of this thing is, though, right? You have no idea what the mass of this planet is. But you're on its surface, and you take out a 1 meter string and a 5 kilogram mass, and you make a pendulum, and you set it moving, and you want to figure out what the mass of the planet that you're standing on is. Remember that the force of gravity is mg is equal to gmm over r squared. So here we know that our g is actually gm over r squared. Our pendulum has a period of 2 pi over L over g. Therefore, if we wanted to find the mass, we could square everything. We could get that g is equal to 4 pi squared L over t squared, but g is equal to gm over r squared, right, is equal to this stuff. From this, we would get that we could measure the planet's mass as having 4 pi r squared over g t squared. We could take out our pendulum, assuming we knew the radius, and measure this and get a mass. Now the radius of the Earth is 10 to the 6, 6.4, so divide that by 3, that's like 2 times 10 to the 6. So this would be 10 to the 12th, g is 10 to the minus 11, so this is going to be 10 to the 23rd, pretty close to the mass of Earth. Who knows? You can do it yourself if you wanted, using the numbers I gave you, because the only number you really needed here was r, and you have r, that's the radius of the Earth. You have L as 1 meter. I guess, I don't know what the period, you could use a 1 second for the period, who knows? Okay, if you really wanted to do this. But just having a rock and a piece of string, standing on a planet that you knew the radius of the planet from taking a picture as you came in, you could find the mass of that planet. Is pretty cool. Again, this is assuming a spherical uniform density planet and blah, 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 but it's not bad. It's going to give you a pretty good answer, pretty close, which is cool. Okay. This is a pretty good exam problem, maybe a little too hard for a quiz problem, but yeah, this is about what we do with pendulums, because we only have one equation really. We have the period. So there's not a whole lot going on here. All right. As I said, the physical pendulum is 2 pi I over mgr. And that's the equation that I want you to remember. And all we've done so far is we figured out I for a point mass and R for a point mass. And so now we need to talk about physical pendulums. And the difference between a physical pendulum and a simple pendulum is a physical pendulum can be any object, rotating at the pivot point. So in this first example, I want to take a uniform rod, length L, that's set to rotate around one end. And we started off at B is 5 degrees or whatever, something less than 10. So we're in the small angle approximation. What is I of a long, uniform, thin rod rotating about one end? That's ml squared over 3. The radius of gyration, r, is the distance from the axis of rotation to the point where gravity is being applied. Okay? So here, we know that gravity is being applied at the center of mass, and the center of mass is at the halfway point. So r is L to the half. Let's put these into our period. Okay, this is where the force of gravity, mg, is being applied. So this r is L to the half. That's our torque. Our lever for our torque is L to the half. So this is 2 pi times ml squared over 3 divided by mg L to the half. And this becomes M's cancel, one L cancels, a 2 comes to the top, and I get 2 pi, 2/3 L over G. And notice, if this was a simple pendulum, we would have gotten 2 pi L over G was our T. So this actually has a shorter period. It actually rotates faster than a normal pendulum, which is pretty cool. So, but the main takeaway here is that for a physical pendulum, we have to consider the moment of inertia of the object, and we have to consider the radius of gyration. We have to consider where the center of mass of the system is, of the thing that's acting like a pendulum. We have to find its center of mass, and that is where the force of gravity is being applied. Okay? Seems pretty simple. I'm going to skip this because I just went over that. But let's look at a kind of fun, I think this is a cool problem. I wish it was in your book. It's not. It's in the university physics book. But I like it, and we're going to do it as an example of how you could use a physical pendulum. And then we're going to talk a little bit more about a kind of more complex example of a physical pendulum. So imagine you went out and you found T-Rex footprints. And you can look at these footprints, and you know that the stride length, the length from the time that it puts its left foot down to the next left foot down, is 4 meters. Okay, and you know from the bones that the length of the leg of a T-Rex is 3.1 meters. So you could figure out from this how fast a T-Rex can walk by modeling its leg as a physical pendulum. How? How do we do that? Well, we need to figure out how long did it take for its left leg to go there and then back, right? Because we assume that it was here and it swung back, and then it picked it up and it put it forward. So 1 full period is the time from left leg to left leg. So if we can find the period, we can find V as this length over the period. Well, the period of a physical pendulum is 2 pi I mgr. And if we look at our, our T-Rex, which I can't draw tonight, with these big legs, right? I'm not going to draw it. But we assume that its leg is, a uniform rod with a length of 3.1 meters. And we also assume that its center of mass is right here at L to the half. So I for its leg is going to be ml squared over 3, because it's a long uniform density rod rotating about one end. And the radius of gyration is the length to the point where gravity is being applied, which is the center of mass, which is L to the half. So again, just like before, we get ml squared over 3 mg L to the half, which gives us 2 pi 2/3 L over G, assuming it's on the surface of the Earth and L is 3.1. Let me figure out what this is. 2/3 times 3.1 divided by 9.81. Take the square root of this answer, times 2 times pi. I get 288. So I get 2.88 seconds, okay? If I take this 4 seconds and divide it by 2.88 seconds, I get 1.38 or 1.39 meters per second, which is about 4 miles per hour, maybe. Somewhere around there. Okay. So from this, you can see that this tells you that if you could model the leg of a T-Rex as a physical pendulum of a uniform density rod, you will get about 4 miles per hour, the same as a human. And that's not too bad. Can you measure the T-Rex leg? Could you measure your leg as a uniform density thin rod? No, probably not. Probably way more complicated, but you're going to get close. So if you imagine swinging your leg back and forth like a pendulum, yeah, then probably pretty close. However, in order to do it more correctly, what you would have to do is you would have to figure out the different moment of inertia of the different parts of your leg, or the different parts of the T-Rex's leg. So I want to show you how to do that when I isn't simple. And one thing we already know, we've already found that if we had a rod, right, with a long thin rod that was length L and mass M, that we got that T was 2 pi I over mg r, but r was L to the half and I was ml squared over 3. And so this gave us that it was 2 pi 2/3 L over G. So now let's imagine that instead of one rod, we have two. So we have two exactly the same rods, but each has half the mass and each is half as long, right? And they're stuck together. So if we're going to find the moment of inertia and the radius of gyration of this, we need to look at this again, okay? Now we know that when they're stuck together, the center of their mass is at the center of them. So we know that R is going to be L to the half. But I is where we're going to have the trouble, because for one rod is the ML over 3 if it's rotating about one end. But for us, this L is L to the half and this mass is mass to the half, right? So I really need here mass to the half times 1/3 times L to the half squared. And so this first rod gives me L to the 4th over 3, so that's L to the 12th, M L squared over 24. For my second rod, and this is where things get a little weird, okay? So the second rod is rotating at a distance L to the half away, but its center of mass is actually at a distance of 3/2 L away, right? Because this is sorry, 3/4 L away, okay? From the axis of rotation. We have something that we learned about called the parallel axis theorem that says I of the center of mass plus md squared is the moment of inertia about any parallel axis. So any axis parallel to the axis going through the center of mass. The center of mass for anything, any uniform rod, I should say, is ml squared over 12, okay? So let's do this for this guy. Remembering that mass is mass to the half and L is L to the half. So this would be m to the half times 1/2 times L to the half squared. Sorry, times 1/12 plus md. And d is going to be 3/4 L squared. So really fast, this is 4, 48, 96. So this is ml squared over 96. This is 9 over 16. Okay, 9/16. And if I want to turn these all into 96s, 4 times this. So if I add everything, this would be plus 4 over 96 ml squared. So what I get is I get 14. Oh, sorry. This would be 6. So 54, 54, 58, 59. Is that right? Let me double check myself. 9 over 16. And 6. What I should get is I should get ml squared over 3. So I should get a third, which would be 32. So somewhere my math is wonky. I think I forgot it too somewhere here. I did. I forgot that this mass is mass to the half. So this becomes 32. And everything works now. Okay, so this is equal to, so this right here is the moment of inertia of the first rod. This is the moment of inertia of the second rod. If I multiply this by 3 on top and bottom, I get 1 plus 27, which is 28, 32 over 96. 3296 ml squared, which is ml squared to the third, okay? Now my t, again, t is 2 pi I over mgr, and this is 2 pi. This is ml squared over 3. This is mgl over 2. So this is 2/3 L over G again. Same exact answer. But you can see what I had to do here is I had to figure out the moment of inertia by figuring out the total moment of inertia of both rods together, and then find their radius of gyration. So the algorithm here is you got to compute the total moment of inertia. You may need the parallel axis theorem for something further away. So you could imagine a thin rod with maybe a sphere on the end, rotating here. And you would have to find the center of mass, a sphere, solid sphere rotating about its center of mass, plus d. Or you could find maybe this is a string with 2, or a rigid rod with 2 point masses on it. And imagine these are at half and half, and these are equal. So the center of mass between them is going to be at whatever this is, 3/4 L, and these two M's are there, right? Sorry, my dogs are barking because they're crazy. The next thing that you have to find is the radius of gyration. And that is just the point that the weight is acting. So on a normal thin rod, the radius of gyration is at the center of mass, and it's empty. Yeah, I'm so sorry about my dogs. I think my wife and son just got home. Maybe we can give them a second. So the radius of gyration is the point at which the force is acting to create this torque that causes the rotation. Okay? And therefore, you may need to confine, or you may need to compute where the center of mass of the composite system is. We probably won't do any of this. I'm just putting it out there for you, so that you understand what you have to do for more complex physical pendulums. You have to find a total moment of inertia. You have to find the center of mass of the whole system to compute R. And then it's just simply the period equation. Not too hard. So one last thing I want to talk about is I want to talk about a couple of well, at least one kind of cool, weird thing that you can research. And that is, you can research what's called a Foucault pendulum. We don't actually have the math to study it right now. When you do vector analysis, you will. And essentially, what you have is a Foucault pendulum is what you see if you go to Griffith's Observatory, right? A lot of places have a huge pendulum that's like a ball that's sweeping back and forth across the floor, and the floor's usually got sand, right? And this is a huge pendulum, And throughout the day, it swings. And as it swings, it slowly changes its orientation. And what that's showing you is it's showing you the rotation of the Earth, showing you the Coriolis force. We don't have the math to really talk about that in this course. You'll talk about it if you take a classical mechanics course. But it's worth reading about, looking up. It's kind of cool. It shows the rotation. It shows you that the Earth is rotating below you, which is a really neat experiment. There's a few associated experiments that are worth looking into. One of them, there was a guy that noticed during an eclipse that a Foucault pendulum seemed to speed up or slow down. I don't believe his data. I think the consensus is that the error was due to experimental error, even though he saw it 3 different years. It's kind of cool to look up, though. You can look up eclipse and pendulum and read all about it. It's pretty cool that NASA and a bunch of other people have tried to replicate his experiment in case they were right, because if it was right, something really, really weird was going on and something crazy was happening with gravity. But I think in the end, it ended up that they're pretty sure it was just experimental error. So that comes back to another thing that I wanted to talk about, since this is our next to last lecture, is everything we've done in this course has been about making simplified models that you can use to model reality and make a prediction about the movement, the displacement, the velocity, the acceleration, the energy of a system, and get some useful information out. And as you've probably seen, on a human scale, it works pretty well. On a micro scale, our errors start creeping in really bad. We just aren't accurate enough. Our numbers aren't accurate enough. Our models aren't accurate enough. We don't have enough information, or we've oversimplified our models. Using a model like friction is mu times n. I hope you realize that we're throwing a constant on there because we don't know. We're hiding all the physics behind a constant. In these restoring force, we're saying, oh, the spring's a K. We're hiding a bunch of physics in there. That there might be stress, there might be strain, there might be materials, there might be, all sorts of forces acting that if we were really, really careful and really smart, we could get a more accurate prediction. And I started off, I think I started the course off by talking a little bit about that. And really in science, it's not whether you're right or wrong, it's how accurate your observations are. And are they within your need? It's hard to tell what a 1 Newton force is. So pretty much being within an accuracy of 1 Newton's fine. If you're making pills that treat someone's cancer that could kill them, you might want to be within a milligram. So basically, we make predictions in the class, we make predictions in actual science, and there's a certain amount of accuracy, and then there's a certain error associated to that accuracy, right? There's a scale factor of accuracy, I should say. And the quest, as you guys move forward in your education, the idea is, as you take your more advanced science classes, you're going to learn how to deal with more and more of those hard things in the models. You're going to learn better ways to deal with friction, ways to deal with other forces that we've ignored in this class. So basically, we've learned a lot in this class. We've learned a lot of simple concepts that work in a general sense, and the rest of your science is going to be refining those models, finding ways to deal with things like friction, finding ways to deal with air resistance, finding ways to actually deal with non-ideal fluids or gases. And it's a lot of fun. It's hard work and hard math because I had someone tell me once that the fun part of research is that all the easy stuff is done. But you got to start somewhere, and you got to understand the easy stuff before you start the hard stuff. So next time, we're going to go through oscillating systems. It's going to be a lot of going back over the blocks sliding back and forth, and then we're going to have the blocks sliding back and forth, but we're going to add friction. And we're actually going to deal with phase angles and some things like that. And then we're going to see how we can turn a system of like a block sliding into things like a, I once had a problem on an exam of a buoy out off Newport Beach going up and down with the tides throughout the day. So things like that, how you can turn these models, these oscillation models, into real world models. We're going to have a few of those, and we're going to talk about, like I said, friction. The fun thing about friction is, obviously, if you have something that's moving periodically, you start adding friction to it, it slows down and eventually stops. So the periods get longer and longer and longer, and how we're actually going to go through that. I want you to watch that video because I'm going to take you through the full differential equation for damping. Your book just kind of gives you the angular frequency. It gives you omega, or if there's friction. And I really hate that they do that, because while it's a little hard to understand, it's better to try and understand it than to have an equation thrown at you and just told this is what it is. And if you are a little curious about differential equations, you'll learn a lot about differential equations from that derivation. That being said, we're just about done. I don't know why this semester felt like a lot. I feel like my head is full of physics, and I can't imagine how you guys are doing. So I'm glad we're at the end. I hope you've learned a lot. I hope that you got more out of pendulums than just T is 2 pi over the square root of L over G. Hope you realize that you now know a lot, and you can really, really, really dig into a pendulum and understand all the different things that it represents and how it's put together, and how to mathematically model, and what a mathematical model means, and how to show or how to learn valuable insights into what a pendulum's doing, even for a super simple thing like a pendulum. Anyway, yeah, hang in there. We're almost done. One more lecture this week, and probably a homework video this week too on fluids. Definitely a homework video on fluids. Fluids are hard. And then we're on to our final, and we're done. So thank you guys. Stay healthy. I'll see you next time.